Hello everyone and welcome to this video. So in this video we are solving a test, and that test is related to the chapters of kinetic model of matter and the transfer of thermal energy, but not the entire chapter in that even. It's just conduction and convection. So radiation is not part of this test, and this is a test that we had conducted in school, and now we'll be discussing this. So let's start with the MCQs first. Question number 1. The diagram shows a radiator heating the air in a room. What is the name of this process? So there's cool air going in, and there's the hot air which is rising above here. So what is the name of this process? It's very straightforward. This is convection, right? Because the cool air is going in and it's rising as hot air. Question 2. Which statement describes the transfer of thermal energy in a liquid by convection? So in convection, a decrease in the density causes the heated liquid to rise. This is true because temperature increases, volume increases because of expansion, density decreases, and this causes the liquid to rise, which is option A. Question 3. Fiber is used for home insulation in a cold country as shown. Heat cannot escape easily through the ceiling because the fiber is a good insulator, right? It's used for insulation, and any insulator basically traps air, and that is how it prevents heat loss by both conduction and convection. Question 4. The diagram shows a glass tube filled with water and suspended above a bench. Water is free to circulate around the tube. At point P, there is a convection current moving in a downwards direction, at which point is the tube heated to cause this convection current. So given this arrow like this, I can also complete this entire loop. So the water must be moving like this, and we know that wherever heat is provided, temperature is going to rise, volume is going to rise, density is going to decrease, so it's going to overall rise above. So from where is the water rising? It's very obvious that that's A. So it must have been heated here so that the water rose above this point. Question 5. Some gas is trapped in a closed container. Gas is cooled and the volume is kept constant. What happens to the gas molecules? So if the gas is cooled, this means temperature is decreasing, volume is constant, so it's going to talk about pressure basically. So they collide with the walls more often. This is not true because if temperature decreases, the pressure is also supposed to decrease. What happens to the molecules? Molecules do not contract themselves, and here even the gas cannot contract because the volume is constant. They get closer together. This is also not true because volume is constant. The correct answer is D, that because temperature is a measure of the average kinetic energy, the decrease in temperature means that they move more slowly. Question 6. Which row describes the arrangement of particles and the forces between particles in a solid? So arrangement is regular, forces are strong. That's option A. Question 7. The bonus question. The pressure of some trapped air is varied, mass and temperature of the trapped air remain constant. Which graph shows how the volume of the air varies with the pressure P? So we know that pressure is inversely proportional to volume. So one way that the graph can be drawn is like this. So if you have pressure here, volume here, the graph for any inverse proportion looks like this. But the problem is that if I look at any of these options, I don't have a graph like that. This one seems close, but on the x-axis it has 1 over v, whereas actually it's supposed to be v. So what is the other possibility then? The other possibility is this, that I say that let me take the entire 1 over v as a new variable z. Now aren't p and z just directly proportional? The answer is yes. So according to that, the graph for direct proportion, because z what I've taken is basically 1 over v, is pressure and 1 over volume. So this is supposed to be a straight line, hence A is the correct answer. Let's move on. A teacher shows an example, a class example of 3 states of matter. These are a solid metal block resting on the bench, a liquid in a glass beaker, a gas in a clear balloon, and in the lab. 4.1 represents the arrangement of molecules. Complete 4.1b to show the arrangement of molecules in the liquid. So if I see here, you have a 4 rows and 4 rows and 5 columns arrangement. So for a liquid, you will just make this slightly more disordered, right? So you can do something like this, slightly playing around with this. So you can do something like this, slightly playing around with this. So something like this, where you still see some regularity, but overall it's less ordered than the solid. This is fine. The other possibility is you can also make clusters, which is a diagram that some books use. So for the gas you are supposed to have these really far apart with no apparent arrangement. So that's this. B1 in the list below, draw a ring around the state of matter that is easiest to compress, that is gases. So this is the ring. In terms of its molecules, explain why the state of matter is the easiest to compress. So why is this the easiest to compress? So you'll just say a couple of things. First of all, always remember to mention intermolecular forces in your answers. So you'll say that there are non-existent intermolecular forces. I'm writing this as IMF, intermolecular forces. Particles are very far apart. So the space between them can be reduced easily, or you can say that so they can be brought closer easily. Next question. Figure 4.1 shows a cylinder with a piston that contains a gas. Part A, a liquid occupies a much smaller volume than a gas which has the same number of molecules. Explain why there is this difference. Again, we have to talk about intermolecular forces. So I would say that as compared to a gas, liquids have stronger intermolecular forces. So the particles are closer together. Occupying a smaller volume. The volume of the gas changes from V1 to V2 as the piston moves into the cylinder. This increases the pressure from P1 to P2. The temperature remains the same. State the formula that relates V1, V2, P1, P2. So P1 is the old pressure, V1 is the old volume. So P1 V1 equals to new pressure times new volume. So P1 V1 equals P2 V2. Initial pressure of the gas in the cylinder is 1.2 into 10 to the 5 pascals. Initial volume is 100 cm cube. Cross-sectional area is 5 cm square. Piston is pushed in a distance of 8 centimeters. Calculate the final pressure of the gas in the cylinder. So I have old pressure, old volume. I am given the cross-sectional area of the piston and it's pushed in from this initial position. So I can also find the new volume and then I can find the final pressure. Okay, so let me also just draw on this diagram. What this means is that the area of this face is 5 cm square. And this is pushed in a distance of 8 centimeters. So maybe if it's pushed in, it comes to this position like this. So let's say this is 8 cm. So if this is pushed in, you can see that 8 times 5, the cross-sectional area times the height basically tells you how much the volume decreases by, right? So 5 times 8, this is 40. 5 times 8, this is 40, and this is that formula that you study in O-level math, which is that the volume is cross-sectional area times height. But this is not the final volume because initially the volume was 100. So all of this is 100. So out of 100, if this is 40, right? If this is what it has decreased by, so the remaining is 60. So 100 minus 40, that is your V2, right? Which is 60. So from here, you'll just solve this. So P1 is 1.2 into 10 to the 5, V1 is 100, P2 is what I need, and the new volume is 60. Again, no need to convert the volume. Some of you might say that this is cm, this is cm, but the idea is that even if we do convert to meters, it would not make a difference. Whatever we multiply or divide by for the conversion, they would cancel out on both sides anyway. So then I just find P2. So if I am not wrong, P2 turns out to be 2.0 into 10 to the 5, and that is basically by rearranging, right? So just cross multiplying by 60, so that's 1.2 into 10 to the 5 into 100 divided by 60, which is this. Explain using ideas about molecules why the pressure of the gas changes. You can obviously see that the pressure is increasing, and that's because the volume is decreasing. But that's not what you have to say, because the examiner says using ideas about molecules. So you will say that there are more frequent collisions with the walls of the container, right? So in this case, with the walls of the cylinder. Let's now go on to the next question. Now this last question, 3.1, shows a metal coffee cup on a metal warming plate. There's a small electrical heater inside the warming plate that keeps the plate hotter than the coffee, so that means that heat is continuously being transferred from the plate to the cup and the coffee. Describe how heat is transferred through the metal and then to all of the liquid in the cup. So being a metal, we know that the more dominant method of heat transfer would be free electron movement. I have to describe that first. So I'll say that electrons move from the hotter to the colder end, to the colder end, and transfer energy to the atoms there, by collisions. This is basically the answer to the first part of the question. And then to all of the liquid in the cup. So for that, I basically need to talk about convection, because that's going to warm up all of the liquid in the cup. So I'll say that the liquid near the bottom heats up and expands. Right, so this is the increase in volume, and then it becomes less dense, right? So density decreases, causing it to rise. And then the colder, denser liquid at the top falls, or you can say sinks, setting up a convection current. All right, next one, part B. A cup of a different shape is placed on the same heater as shown. The two cups are made of the same metal and contain the same amount of coffee. Explain why the coffee in 3.2 is not kept as warm as the coffee in cup in 3.1. So in between you have air, right? And what do you know about air is that it's a poor conductor. So air is a poor conductor, or you can also say it's a good insulator. Both of these mean the same thing. Explain which is a better conductor between solids and liquids. So solids are better conductors. Since the strong intermolecular forces cause or you can say lead to very little spacing between particles. So the idea is this, that the pushes between the particles are very efficient, and then those are passed on. So that was this test, and I hope that this basically solved all of your queries. So like this video, comment if you still have any confusions or questions, and subscribe to the channel for more content like this. And I'll see you in the next video. Bye.